Hello, everyone. My name is Muhammad Attahir Jibril. I'm a PhD student at the TU Ilmenau in Germany, and I'm going to present to you our work on update handling for heterogeneous H2TAP. The work was done together with Hani Al-Sayeh and Alexander Baumstark under the supervision of Professor Kai-Uwe Sattler. And the work was published earlier this year in EDBT. So to start off, we looked at graph workloads as being broadly classified into two, the transactional and analytical workloads. So transactional workloads are basically insert, delete, and look up graph objects. So graph objects being nodes and relationships. And of course, they include traversing the neighborhood of a node. And they are by nature relatively short running and latency critical. On the other hand, analytics are relatively longer running, and a lot of times they are offloaded to accelerators such as GPU. So they include traditional algorithms like the BFS, SSSP, PageRank, and so on and so forth. So our focus in this work is a mixed workload of concurrently running transactional and analytical workloads, which is also referred to as hybrid transactional analytical processing, or HTAP for short. So the work is to develop solutions to tackle or to handle HTAP graph workloads. So we made some design space exploration. We considered three alternatives: single instance CPU, single instance GPU, and separate instances. And I'm going to touch a little bit on each of them, along with the advantages and disadvantages of each. So the first alternative is to have a single instance CPU. So here we have a single instance of the graph on CPU, and we run transactions and analytics concurrently on the instance. So of course, the advantage of this approach or this alternative is that it is easier to manage in the sense that we don't have to synchronize between different instances of the graph data. On the flip side, the disadvantages are we cannot make optimizations for transactions and optimizations for analytics on the same graph because the optimizations for each of these workload types are different and sometimes even opposing. So we are not able to make workload specific optimizations. And also because the single instance is on the CPU, we cannot benefit from performance speed up from accelerators such as GPU. The second alternative is a single instance GPU, where we have a single instance of the graph entirely on GPU, and we run transactions and analytics concurrently on the GPU. Yeah, this is somewhat similar to the first alternative, but it's even more. It has even more issues because of the peculiar nature of GPU. And the third alternative is to have separate instances, one on the CPU and the other on the GPU. So we make optimizations on the CPU instance for transactions and optimizations on the GPU instance for analytics. Yeah, the advantage of this approach is, unlike the other two approaches, we can make workload-specific optimizations because we have different instances for each workload. And also, we don't have performance interference. Yeah, unlike the having a single instance where you don't have performance isolation. And of course, we get to benefit from, we get to leverage GPUs for accelerated analytics. Yeah, the downside is, of course, we have to synchronize between the instances in case of updates. So this is the third, this third option is the option that we chose. And it's also called heterogeneous HTAP, which is an HTAP architecture based on modern hardware where you assign each processor to the workload that suit it the most. So of course, yeah, this is not a problem-free approach. There are challenges that we need to tackle. So the first is propagating updates from the CPU instance to the GPU instance. And the update propagation should be done with as minimal overhead as possible, such that we don't drastically reduce the overall performance of the entire system. The second challenge is to meet HTAP freshness requirements. So this means that we should execute analytics on the most recent version of the graph data. And of course, the third challenge is to guarantee consistency between the two instances, the instance on the CPU and the instance on the GPU. So put together, all these are what we refer to as update handling in the paper. This is a short overview of the update handling approach that we took. So at the center of the approach is a delta store, which is just a differential store that we buffer updates from transactions before we propagate them to the GPU for analytics. So it has two phases basically. We have the update storage phase on the right, on the left, and the update propagation phase on the right. So during the update propagation, this is when transactions are updating the main graph and also persisting their updates at commit time. So they also append deltas to reflect the changes or the modifications that they made to the main graph. And then the update propagation phase is triggered as soon as we have analytics to execute. So when we have analytics to execute, we propagate the changes, which are in form of deltas in the delta store, to the graph instance on GPU. So as for the update propagation phase, the execution flow depends on the data structure that underlies the graph itself on GPU, whether it's a static data structure or it's a dynamic data structure. Majority of the works on GPU-based graph analytics use static data structure, specifically the CSR. So if you have a static data structure like the CSR, so the update propagation would start with a scan of the delta store here. And then when we scan the deltas too, we get the deltas that are relevant for the update propagation, for the particular update propagation cycle. And we devise a way to merge the deltas into the old CSR, and we get a new up-to-date CSR. Afterwards, we transfer the new CSR to the GPU to replace the old CSR, and we execute analytics on the fresh version of the graph. On the other hand, if we have a dynamic data structure, it still starts with the scan. The update propagation starts with the scan. We scan the deltas and get the deltas that are relevant for the current update propagation cycle, and then we transfer only the deltas. That's against the other scenario where we transfer the entire CSR. So we transfer only the deltas, and then we update the dynamic data structure in place on the GPU. So this is a short overview of the update handling approach that we made use of. So going to the evaluation aspect of our work. Starting with the setup, we made use of two machines. We used a GPU server and a PMEM server, persistent memory server, because our graph database, which is based on CPU, is based on persistent memory. So in addition also to the implementation of the delta store in DRAM, we also implemented the delta store in PMEM, just to have to quantify how much the overhead is going to be if you have a PMEM-based delta store. But I should mention here that our approach is orthogonal to persistent memory, so it's not affected by persistent memory at all. So for the data, we made use of the LDBC SMB dataset and the Graph 500 dataset, and the workload we used insert and delete like queries that are similar to the LDBC SMB queries. And for analytics, we used some of the algorithms specified by the LDBC Graph Analytics benchmark. We made a couple of evaluations. We compared our approach, which we represent here as delta FE, with a baseline approach that we represent here as delta I. And we considered different operations, so in the insertion of a node, deletion of a node, insertion of a relationship, and deletion of a relationship, as well as the mix of all these four types of operations. And we also considered updating nodes with low degrees, which is denoted by a low deg here, and also updating nodes with high degrees. So in summary, what we are going to the conclusion that we are going to take from this figure is that first, our approach, the delta FE, outperforms the baseline approach. This is one, and then secondly, we see that the performance of the baseline drops when we are updating high degree nodes, whereas the performance of the delta FE is not affected at all by the degree of the node. So irrespective of the degree of the nodes that you are updating, the performance stays the same. So this is with regards comparison with regards to the transaction time. So this gives us a picture of the overhead that we incur as a result of the update storage, of appending deltas to the delta stores. So this is about the update storage phase. So the next is the update propagation phase, and the comparison is also the results of the comparison is similar. we see our approach is faster than the baseline approach, and also the baseline approach is influenced by the degree of the nodes, whereas our approach is not influenced by the degree of the nodes. So we also took a closer look at the components of the update propagation, the components of the time components of the update propagation, because the update propagation starts with a scan of the delta store and then the merging of the deltas to the delta structure, to the data structure representing the graph. So here we have, so we can see from this three sub-figures here that there is also a correlation between the number of deltas that are stored in the delta store and the time components. So we use this to and developed some cost models, and we implemented an adaptive approach to update handling, but it's not part of this paper, so I'm not going to talk about that. We also compared with single instance of a graph, an approach that uses single instance of a graph on CPU. So we used the subtle-done data structure, and we compared the execution time of analytics on CPU using the subtle-done data structure on the one hand, and on the other hand, we compared the sum of the execution of analytics on GPU and the overhead of update propagation using our approach. And we can see that, especially for the longer running algorithms, because we compared with 3 BFS, PageRank, and single shortest path, our approach outperforms the single instance CPU approach, especially for longer running queries. But for shorter running queries like BFS, the single instance outperforms our approach, because the performance difference you get between GPU and CPU is not much to warrant update propagation. And lastly, we also compared with a direct translation of existing relational approaches for graphs. So we just directly translated them for graphs. And we can see also our approach outperforms a direct translation of existing relational approaches to graphs. Yeah, so in short, this is just a short overview of the work that we have done. And the details you can refer to our paper in EDBT. So in conclusion, yeah, this is a fast and efficient approach for handling updates in heterogeneous H2TAP settings for graphs. And our approach has minimal overhead, and it guarantees consistency and also meets freshness requirements of H2TAP. And from the evaluation, we've seen that our approach outperforms existing approaches. So with this, I come to the end of my talk, and thank you for listening, and I would be happy to answer any questions.
Questions? Questions from the room?
Well, I'll have one.
Okay.
I wasn't going to go here, but since no one's asking questions, you didn't say a thing in your comparison to the CPU and the GPU numbers of how optimized the CPU code was. I see this all the time. When we look at the performance between a CPU and GPU, we expect the GPU to be faster because the memory is faster. So I expect speedups of 3 or 4. When I see a speedup of 10 plus, then I suspect that, what did you do to optimize them? You know, if I go to the GPU, I write everything from scratch from CUDA. If I go to the CPU, I take whatever the heck code I have already. So it's not something to go into deeply here, but it's as you move forward with this research, please pay real close attention to how you benchmark and compare across architectures. Because, you know, you didn't say a thing about it. What did you do to optimize the CPU? Okay.
Well, let's hear the answer.
Well, we know the answer. I just don't need the microphone. That's about me.
Yeah, so so in the comparison, we used the existing code of the authors. So we did not. It's not our implementation. So we use the existing code of the authors. And the idea about the comparison is to show that just because you have an efficient implementation on CPU, that doesn't negate the benefits that you get with a GPU. And if you have an efficient update handling approach, you'll still get the benefit of using a GPU and also propagating the updates. Yeah.
Right. One question from. Back to the. working. Turn it until it's green. You. Oh, does that work? Yeah. I think we have.
Is this working? You can try the handheld.
Can you go back to the first slide that had performance numbers?
Okay. Yeah, this one. Can you see this?
Yeah. So this is saying it took 15 seconds to insert 200,000 nodes. Is that right? For high degree delta?
Yeah.
Okay. And then the last one is your actual proposed solution, I guess, delta FE high degree. This slide is a little confusing. I wasn't sure what the heck was going on.
So the high degree is if you limit the updated nodes to nodes that are just that have high degree. This is the high degree. So the low degree, if you limit the nodes that you're updating to nodes with low degrees, yeah.
But if you're inserting nodes, then they have 0 degree, right? They're just blank nodes with nothing, or?
Sorry, can you repeat the question?
If you're inserting nodes, the nodes don't have any relationships, right? They're just.
Yeah. So in the evaluation, so in the insertion of a node, when we insert a node, we insert relationships alongside the node. So we're not just inserting a node with empty relationships.
Okay, that makes more sense. Okay, thank you.